Hello everyone. In this video, we will discuss Fourier series of a square wave. Joseph Fourier is a French mathematician. He stated that all waveforms consist of the sum of sine or cosine functions, or we call it the sum of all sinusoids. It seems odd that a straight line is the sum of all the trigonometric functions, in this case sine and cosine, but it was proven to be true. I would like everyone to take a look at the diagram that I illustrate here. This is the graph, okay? And the sum of all the sine graph is also the sum of a lot of sine graph, a sum of more sine graph. And the more sine graph that you have, you turn this into a straight line, okay? And the Fourier series for this is equal to fx equal to 4 over x multiplied by sine of x plus 1/3 sine of 3x plus 1/5 sine of 5x plus 1 over 7 sine of 7x, and so on. And note that what you have in here is only the odd harmonics with the term for the sine. Okay, so keep that in mind. So a square wave is the sum of all of the sine graph, and we only consider their odd harmonics. Alright, so let's see the illustration that I have for everyone on this side. Okay, so first of all, take a look at the sine graph. Okay, so I repeat the Fourier series right here, and I will analyze to everyone one graph at a time. So this one here, I only have it with fx equal to 4 over x times sine of x. Okay, so keep that in mind. So this one is only for sine of x times 4 over pi. So we are familiar with this already. You see, it's just a sine curve. We call it a curve. And on this graph, what I would like everyone to recognize is that I am adding 4 over pi of sine x with 4 over 3 sine of 3x. Okay, so the next odd harmonics of sine. So we call this waveform is synthesized and combination of two sine graphs. So this one I have two sine graphs. You see how it's synthesized into this? So that's the shape of the two sine graph. And then I start adding on two more terms to this. Okay, so in this case I will have 5 terms. I will have the first term as with the third harmonic, the fifth harmonic, the seventh harmonic, and the ninth harmonics. Then I have 5 terms, and the shape of my sine graph turned into a shape like this. Okay, so the next one is I have 14 terms. You see that it shrinks into smaller and smaller. Here I have 20 terms. Okay, 14 terms, 20 terms. And continue on till I have increase the term to 26 term. And then I will have to 36 term. And then I have to 50 terms. And you see that it's almost turned into a straight line. Okay. So all the sum of the sinusoid turn into this shape, and this is called a square wave. Okay, so how do we prove that? So let's work with a few examples, and then we can prove that the graph that we have right here is the sum of all of our sinusoids. Okay, so this question asks me to determine the Fourier series of this waveform, and right away you when you look at this waveform, you see that it is a straight line, purely a straight line. So how do we consider that it's a sum of all the sinusoid? Okay, but we are going to prove it in the next few steps. So step number 1 is we have to find the equation. We have to analyze to see if our waveform is even or odd, or is halfway symmetry, so that we can define its Fourier series. Okay, define its Fourier series before we can find certain terms of that Fourier series. So this question asks me to determine the Fourier series with 5 terms, okay, of the following square wave. We set the square wave, and we have to integrate with the unspecified terms n. Okay, so this function fx, okay, starting from 0 to 2 pi. So right here, half of this should be pi. And then on this side of the equation, I should have it as negative pi. So it's a good idea to identify our period. And this function is given to me as fx is equal to 1. Yes, it is equal to 1. Right here, fx or y equal to 1. Given that x is less than 0, and then greater than negative pi. Okay? Okay, so in this case, I should say is equal to negative 1. So what I have is, so let's start with the negative function first. So right here I have fx equal to negative 1. Okay, so the number negative 1 is right there. fx here equal to minus 1. Given x from the period of negative pi to 0. So this is what we have. It is a split function, so that we have to have 2 forms of this function. The next one is I have to consider from 1 to when fx equal to 1. Okay, so when fx is equal to 1, given that x is less than pi and greater than 0. Okay, it is a split function, therefore I have to have 2 forms of this function. Okay, so this graph is given to me and its functions are given to me. Okay, so the next step is it's also given me that this function is odd, okay, and it has halfway symmetry. Okay, so I would like everyone to refer to this formulas that I have in our workbook. Okay, so this formula is on page 11, okay, page 12, page 13, and page 13, 13, 14 of our workbook. Okay, 11, 12, 13, and 14 of our workbooks. So these are the pages that involve the essential formulae, the integrals for Fourier analysis, some very important integral shortcut that you can use in the process of integrating using unspecified term n. Okay, so I want everyone to familiar with these 4 pages. Okay, so let's get back to the questions. Okay, so the questions say that it's odd and halfway symmetry. So what you need to do is you need to ask yourself, is this Fourier series having the constant A0, or it has the A term, or it has the B terms? Okay, so to check that, you go to this page and you go to this chart right here on page number 13. On page number 13, it said that if the waveform is odd, has an odd symmetry, then it is it's only have sine term, and if it's halfway, then it's only have odd harmonics. Okay, so the question gave me this is odd and halfway symmetry. So if it's odd and halfway symmetry, then I should not have any of this constant at all. Okay, so in this case, I will have no A naught. Okay, no constant. Okay, what about the AN? No, I don't have any cosine term. Okay, so let's double check again. Alright, okay, so if the function is odd, right here is set odd, okay, it's only have sine term, right? No constant, no cosine, so we indicated that. But it has halfway symmetry, so it's only have odd harmonics, and it doesn't have any even harmonic. Okay, so let's circle what we should have. So that means it should only have the B1, B3, B5, B7, and B9. Okay, so let's get back to our questions. So I will write it down on here. Okay, so for this Bn, this question asked me to get 5 terms. Okay, so I will write it as B1, B3, B5, B7, and B9. Okay, so these are the Fourier coefficients of this Fourier series. Because I need to find those terms. So to find those terms, I have to find the Fourier coefficients. Okay, and those coefficients, because this function is odd and halfway symmetry, therefore I don't have any A naught, I don't have any cosine term, I only have the sine term, and the sine term, the coefficient can only be the odd harmonic because it's halfway symmetry. Okay, so therefore this is a 5 coefficient here will give me 5 terms for this Fourier series. So step number 3 is to look for the Fourier series. Okay, so for us to do that, I would like everyone to turn to page 13. Okay, turn to page 13. So right here, the formulas again, page 13. And on this page 13, we are going to work with these formulas. Okay, we are going to work with that formulas because we don't need to work with A naught. We don't need to work with AN. We only have to find the term B. So we have to work with that formulas. So I will write that formula on this page. I will write that Bn is equal to 1 over pi from negative pi to pi of function fx multiplied by sine of nx in the bracket and dx. So this is very important. I need to use these formulas. And the function is given to me as fx equal to, and don't forget it's a split function, it's equal to minus 1 given x less than 0 greater than or equal to minus pi is equal to 1 when x is greater than or equal to 0 and less than pi. Okay, so I need to write the fx into this equation. Okay, so I will write Bn equal to 1 over pi. Okay, so first of all, I need to fit this function equal to minus 1 into this integral, but I have to split it into 2 because this integral said that I have to go from negative pi to pi, and it is a split function, so I must have 2 integrals. So 1 over pi, okay, from negative pi to 0, which is what I have right here. Let me point that to everyone. From 0 to negative pi, from negative pi to 0, and this function fx is equal to minus 1, so I put in minus 1. And the formula said that I have to multiply by sine of nx dx. Okay. Then I have to take care of the other part of the function as well. So I need to add that with, again, repeat the same formula, 1 over pi multiplied by integral, and this time I have to go from 0 to pi of the function f(x). In this case, it will be equal to 1. Okay, and I multiply that with sine of nx dx. So this is called integral, or integrating with unspecified term n. Okay, so that means you don't know the value for n, but we have to integrate in terms of n. Okay, so let's make a note here. This is for fx equal to -1, and this is for fx equal to 1. Alright, okay, so we have to integrate this. Okay, so it's not that difficult at all. So before we can integrate this, I would like to factor out the 1 over n. Okay, inside the bracket, I should left with integral of negative pi to 0. Okay, I will take -1 times this sine of nx, so I will put negative sine of n times x as the argument, dx. I already pulled the 1 over pi outside the bracket, so in here I should left with adding the integral from 0 to pi of sine of nx dx. Okay, close the bracket. Okay, so I would like to pause a bit and remind everyone that in this case, do you see that you are going from the full cycle from negative pi to pi? Okay, for this part, because the function split into 2, but still including the full cycle of negative pi to pi. And what you did is you integrate that from negative pi to pi. Okay. Alright. So now let's make a note of this. How do we integrate sine of nx dx? How do we integrate sine of nx dx? Okay. And how do we integrate sine of nx? Okay. And also we have to evaluate that from negative pi to 0, from 0 to pi. So don't forget, this is a definite integral. Okay, and we have to apply fundamental theorem of calculus. Okay, so apply fundamental theorem of calculus. So apply fundamental theorem of calculus, it means that you have to evaluate at the upper limit, subtract the value from the lower limit. Okay, so first of all, before we can do that, let's check if I integrate sine of n of x dx, then what do I have? Okay, so again, I will ask everyone to turn to page number 11 of our Fourier booklet. Okay, so here is page number 11. On page number 11, I would like you to look for the formulas that you can use to integrate sine of nx dx. Okay, so I figure out that I can use this formula here. Sine of nx dx is equal to negative cos of n times x as the argument divided by n. Okay, so it's a shortcut, was already here. It's already giving me this formula to work with. So all I do is I will indicate this here that I use number 8 on page 11 of Fourier workbook. Okay, so the same thing, I will put number 8 on page 11. Alright, okay. So let's write that down. So it's 1 over pi. I keep the negative. So this question that saying that the formula said that it will be negative cos of n of x divided by n. Okay, apply fundamental theorem in this case. That means I need to write evaluate from negative pi to 0. I add that with this also turn into the negative cos of nx divided by n, and I evaluate this at 0 to pi. Okay, so the next step is to simplify all of the negative sign. Okay, so I put 1 over pi. Negative times negative give me a positive, so I should have cos of nx as the argument divided by n from negative pi to 0, and subtract cos of nx as the argument divided by n, evaluate from 0 to pi, and I close the bracket. Okay, so now I'm going to apply this fundamental theorem to here. That means that I have to evaluate at the upper limit minus the lower limit. Okay, so Bn will be equal to 1 over pi. Okay, and we have to be very careful here. Okay, so I will apply, make a note, I apply f of 0 minus f of negative pi. Okay, so then I should have cos of n times 0, right, divided by n, and I subtract that with cos of n times negative pi divided by n. So this is the first part. The second part is this. Again, I also have to apply f of pi, subtract f of 0. So I will subtract cos of n times pi divided by n, subtract cos of n times 0 divided by n, close the bracket. Okay, so let's evaluate this. So Bn equal to 1 over pi, and in the bracket, this is what I should have. Okay, so in this bracket, I should have cos of n times 0, so it will be cos of 0 over n, and in this case, I should have cos of negative n times pi divided by n, subtract cos of n times pi, okay, divided by n, and subtract cos of 0 divided by n. Okay, the next step, I would like everyone to see that everything is divided by n. So what I will do is I will factor out the 1 over n. Okay, factor out the 1 over n. Inside the brackets, I will have cos of 0. Okay, subtract cos of negative n times pi, subtract cos of n times pi, and don't forget this is multiplied inside the bracket, so I will have the plus of cos of 0. Okay, so let's see what I have next. Okay, so now 1 over pi times 1 over n, you can write it as 1 over n times pi. Okay, so cos of 0 is equal to 1. Okay, what about cos of negative n times pi? How do we figure that out? So I would like you to turn to our formula, okay, the page with all of these. So I would like you to take a look at number 2 on here. So here's number 2. See that? It said cos of negative n pi will be equal to cos of n pi. Okay, so I will make a note here that I use number 2 on page 11 of the Fourier workbook. Okay. So what we have is subtract cos of negative n pi will be the exact same thing of cos of n times pi. Okay. Subtract cos of n times pi and plus cos of 0, so it turns into 1. Okay. So the next step is to simplify. Okay. 1 plus 1 will give me 2. Okay. And this 2 adding should give me subtract 2 cos n times pi. Okay. Now, what is cos of n times pi? Okay. Cos of n times pi. We have to figure this out. So, n can be any number, any integer. So let's go to our page again. This is the page number 11. And on page number 11, I found that there is a formula number 7, this one right here. Okay. Page number 7 told me that cos of n times pi could be equal to minus 1 to the exponent n, given n equal to 0, 1, 2, 3, 4. So let's apply this formula to our calculation. Okay. Alright. So on here, I will say that this is equal to minus 1. Okay. So I will say is number 7 on page 11. Okay, and this formula told me that cos of n times pi equal to minus 1 to the exponent n. Okay, and n is odd, so I will have cos of n times pi will be equal to minus 1. Alright, okay. So I will have Bn will be equal to 1 over n times pi. So negative 1 times 2 will give me positive 2. So 2 plus 2. In this case, it will be equal to 4, right? And 4 times 1 will give me 4 over n times pi. Okay, so the unspecified term n will be Bn will be equal to 4 over n times pi. And from here, we are going to analyze. Okay, so you need to have B1, B3, B5, B7, and B9. Because the question asks you to find that Fourier coefficient. So let's get back to our chart. Okay, so this question asks us to determine the Fourier series with 5 terms of the following square wave. And in this square wave, it is odd and half-wave symmetry. Therefore, you don't have the constant term. You don't have the cosine term. You only have the sine term. And because it's half-wave, therefore you can only have the odd harmonics. Odd harmonics would be B1, B3, B5, B7, and B9. After you integrate, you find the unspecified values for Bn, which is Bn equal to 4 over n times pi. Now you specify it as B1, B3, B5, B7, and B9. So then what you should write is B1 will be equal to 4 over 1 times pi. Okay, so B3 equal to 4 over 3 times pi. B5